Today I'm going to talk about coding theory and data storage. And it's the first time I give the talk, so you're either in for a good time or not. I hope a good time. I should say right at the beginning that it's joint work with my colleague at Duke, computer architect called Dan Soren, with my postdoc, Alireza Vahid, who is on the market this year, and Georgios Mapouros, who's graduate student with Dan Soren. And what we're going to talk about are memory technologies. Actually, what I'm going to do is I'm going to talk a little bit in general about memory technologies, and then I'm going to pick two of them that we've worked on, Flash and a more speculative memory technology called Racetrack. And I'm going to tell you what we've done there. And along the way, I'll make some remarks about what it's like for a coding theorist to work with a computer architect, because it really is cross-cultural. So here, whoops. How did this? I think I'm going to be made it. I will master the clicker at some point in the talk. So, after a long while, where in memory technologies, basically the same technologies just sort of got better, we've had the introduction of a whole bunch of new technologies. And the good thing about new technologies is that they bring new problems for both computer architects and coding theorists. So here, I've tried to give you the characteristics of the different memory technologies: Flash, PCM, DRAM, 3D DRAM, and Racetrack. I've picked out recording density, whether they're volatile or not. Volatile means that if you take away the charge, do they still continue to retain information? Being non-volatile is good. Being non-volatile is the reason that Flash is taking over data centers. It's not so much that they're more storage or faster, it's that it's less power. You only have to look at where data centers are situated, like by the Columbia River, to know that volatility is important. So the green things are good. What I've highlighted at the bottom is this are the different error models. And so for Flash, the problem is that these little Flash cells, we can only erase them so many times before they lose the ability to retain information. And so we're going to be thinking about ways of extending their lifetime using coding. Racetrack, the source of errors are going to be shift errors. And I'll describe what those do in a minute. So here, I'll characterize conversation with Dan, who, the way that this collaboration happened was that I was giving my coding theory class, and he sent his student, Adam Jakobitz. And what I do in the coding theory class is, in the first part of the class, I teach stuff, and in the second part of the class, students spend time doing projects. And his project was Flash, and out of that project came this collaboration. And it's really an example of a collaboration where we don't actually, at the beginning, speak the same language. I mean, in some sense, when you think about computer memory and how it goes forth into the world, there has to be a collaboration between computer architects and coding theorists for things to actually end up in product and for product to go out into the world. But those collaborations tend to take place in industry, and this is one highly secretive industry. Talking to people at SanDisk about what they're doing is like talking to people at NSA about what they're doing. No information comes your way. So this kind of cross-pollination between coding theory and computer architecture, it does happen in industry, but the corresponding communities in academia are quite separate, and we don't really talk to each other as much as we should. So here's an example. We're talking about Flash. Can you help us improve the endurance? Well, there are endurance codes. Why don't you use one? He says, well, unfortunately, we can't because they don't fit in our framework. So then we start talking about what we might be able to do. And so here, it's really interesting from my point of view because I get to do new things. I get to think about this tree and how properties that we want applications to have interact with coding theory and computer architecture and the physical substrate. One of the things that I've come to appreciate about computer architecture is that, it does many things for coding theory. I mean, first of all, it's a source of new problems. Second of all, it provides a framework in which coding theorists can innovate. And third of all, it has these ways of measuring performance, which in the coding theory world we're not used to, like how fast the common case runs, which is hugely important. So here, what I'm going to do here is I'm going to briefly review Flash and briefly review Racetrack, and then I'm going to go into some detail. So Flash, there are different kinds of cells, Flash cells. There are 2-level cells and 4-level cells and 8-level cells. They're called SLCs and MLCs and TLCs. Actually, really, there are just MLCs. I mean, there's a few TLCs, but the single-level or 2-level cells, they're just multi-level cells where you use restricted functionality. And the life of a Flash cell, it's limited by the number of times it's erased. And so wear out becomes the main drawback. We want to write multiple times before each erase. We don't want your laptop to die before it's supposed to die. If it's supposed to last 3 years, we don't want it to last 2.5. We'd like it to last 3 1/4. So wear out is an objective. And what happens as we fabricate new substrates is that these Flash transistors, they become smaller and smaller. And as they become smaller and smaller, they are less able to tolerate erase cycles. So as the technology gets smaller, the problem becomes more pronounced. So these Flash cells, you can increase charge, although not all increases are possible, and I'll talk a little bit about that. But once you get to the top, there's nowhere else to go. So when you get to the top, you have to erase the cell, you have to erase the whole page of which the cell is a part. And then you can start again. Flash cells have something called program without erase, which is that you can increase charge levels in the cell without erasing.
Reading is free?
It more or less, yeah. So there are 2 things that are actually, so there are complications that we coding theorists don't typically take into account, which are things you're not allowed to do. You're not allowed to do this, and you're not allowed to do that. And in fact, in the computer memory, why they do this, we don't really understand. But this bit is written on a page X, and this bit is written on a page Y in the same block. So that's a strange thing, but that's the way they all are. And what we want to do is we want to take the MLC technology and move it to the right. And it took Dan and I a while to get to a common language about thinking about this lifetime gain or improving endurance. And what we fixed on at the end was this idea that, okay, you buy a flash memory. It's a bunch of cells. What you advertise to the user is host visible capacity. So there's two parameters. There's host visible capacity and there's how long you live. You can take all the cells, you can advertise that capacity, and you can live for L. You can divide the cells in two, you can advertise C over 2, you can live for 2L. So these are the kind of trade-offs you can make. But this is the world. And so we want to normalize the raw capacity and think about how we can use it to achieve different rectangles in this space. Why would we want to do that? Oops. Sorry. Why would we want to do this? Well, over here, you can think about, so you have a certain capacity, it has a certain lifetime. This dotted line is how long your laptop lives. And we actually don't have, or manufacturers don't have that much interest in pushing this out to the right. There are things like embedded systems where we want them to live a much longer time. And so we're interested in rectangles that look more like this. Now, what's going to be interesting is the metric that we use, because you see the area of the rectangle is how much capacity you're advertising and how long it lives for. And we want rectangles with big area. So here you've got 12 times a sixth, which is 2. And over here you've got 1 times 1, which is 1. So 2 is better than 1. So we want to know how well we can do that. That's Flash. And now we're going to talk a little bit about Racetrack. So Racetrack it's a proposal for memory that came out of IBM research and Stuart Parkin, who is now, I think, in Germany somewhere. It has very high density and very fast read and write latency. I think now we... what is it? So the way that you... so here's how I think about it. The data is stored in little magnetic domains that live in this racetrack. There's a read-write port. Actually, there are 2 read-write ports, and the track is in 3 dimensions in a U. But I'm just going to spread it out in a line like this. When I want to read a bit, what I do is I inject current at the side, and the magnetization moves over to the read-write head. The track doesn't move, but the magnetic domain moves over. So that's the current being applied. And sometimes there's no error. Sometimes you get the current wrong, and you lose a bit. Sometimes you don't put enough current in, and you get the same bit twice. So this defines a channel where you have deletions and you have repetitions. And there's prior work in the computer architecture community. There's actually a paper called HiFi in, I think it's in Micro, where they didn't use coding theory to go after this problem. They used additional hardware. They put in actually 2 additional read-write heads. There are actually 2. I'm only showing 1, but there are actually 2 read-write heads on each racetrack. They wanted to put in another 2, which is problematic. And they needed to make, I think, 3 extra reads and a write. And so their energy consumption goes up quite a bit, and I'll show that a little bit later. What we want to do is we want to use coding to get around this problem. I'll describe how we do that. Now, in coding, you use redundancy to get reliability. And in this situation like Racetrack, you have 2 things that you can use coding for. You can use redundancy to identify what error happened, and then you can use redundancy to correct the error that actually happened. And what we do is we do a little bit of both. So we introduce, so our error model is no more than 1 shift every n bits. We actually don't have to worry about bit flips to a first order, although we have, I mean, it is still a little issue, and we have a way of thinking about that. But we put in these 3 delimiter bits. And when we read those 3 delimiter bits, when we see a 0x or an x0, we can tell whether we've got a deletion or whether we've got an insertion. And we're going to preface, we go in between the delimiter bits, we're going to use a very simple code that's able to correct 1 deletion or insertion. And this is the code that we're going to use. So we have n bits, sorry, n entries, and we're going to write bits, ci, with this property that the sum of the sum of the modulated i's is 0 mod n plus 1. They have, and we're going to end up with a code where we only give up, I mean, the rate is asymptotically 1. We only give up logarithmic overhead. That's useful. All right, so that's this. Now you can actually all go home, because we're going to, now what we're going to do is we're going to spend 15 minutes talking about each one. So let's talk first of all about Racetrack. So here we are, we've done this. And these are the magnetic domains. There's domain wall, read-write port, no moving parts, bits stored magnetically, current, new challenges, no error, deletion, repetition. Okay. Now, let me describe the, so we've got this, my goodness, come on. So when you go to information theory and you talk about the insertion and deletion problem channel, it's an old problem. People have studied it for a long time. Actually, Jeff Ullman wrote a thesis in 1965 on the insertion channel. Right? So I mean, this problem has been around for a while. There's work by Dobrushin and Gallagher in the 60s, which is motivated by the Z channel in information theory. There's upper and lower bounds, but there's no exact capacity. If you're thinking about traditional linear codes, you can't do so much, like on this problem, to correct a single shift error. The best you can show that the best possible rate is a half. Actually, the code is really simple. You use that code. You map zeros to 0, 0, and you map ones to 1, 1. All right, what are we doing? So we've got 1 shift error per m minus 1 shifts. And it's easy to encode and decode. How do we do? How does this work? All right, so this is, we separate detection from correction. This is, so let's just, so here we've got m bits, including the delimiter bits. And if we have a deletion in the first m-3 shifts, or a repetition in the first m-3 shifts, then when we get to the delimiter bits, this is what we observe. So we can figure out what happened. It's a little bit more subtle if an error happens here. And I won't explain that in detail, but what happens is we catch it the next time. So, how does this work? Now, when you're thinking about code design and you want to correct shift errors, one of the ways to think about this is to think about it in terms of a graph, right? You have these n-bit strings, and if you make an insertion or a deletion to your n-bit string, you get another one. And so you can make a graph on n-bit strings where you join things if they can be confused. I mean, if two things go to the same thing, then you confuse them. And you're looking for independent sets in that graph. So that's a general framework for code design, but it's a little bit of a complicated framework. And it's too complicated. So this is the, good, that's it. So we're going to do this. And in fact, we're going to choose n to be a power of 2. So how are we going to do this? Maybe I'll say this even on the next. All right, let's go back. Sorry, I'm getting tired of doing all this clicking here. Good. All right. So here, this is the condition that defines the code. And what we're going to do is we're going to hold out the entries CI corresponding to powers of 2. When a deletion or an insertion happens, the parity is going to be off by a certain amount. So, I'm sorry. We're going to hold out those coefficients that are powers of 2. We're going to put the data in the remaining ones, and then we're going to have a parity thing to calculate, and we're going to be able to do that with the powers of 2 that we've kept out. So that's how we encode. Let me, so here, this is an example for n equals 8, so 2 to the 3rd power. So here we've set the positions that are not powers of 2 to the data bits. We calculate the checksum. We calculate the minimum number that we have to add. Remember, n plus 1 is 9. So twice 9 is 18. So we've got to add 2. And that's how we complete the code word. So this is 1, 2, 3, 4, 5, 6, 7, 8. Good. Very good. All right. Done that. All right. Now I'm going to talk about deletions. So here we are. And I'm going to, I've deleted that 0. And I've reduced the checksum by the number of 1s to the right of the deleted 0. How does my error correction work? I start with the n-1 bits that I've observed. So I've taken that red 1 out. I calculate the Hamming weight. That's 3. I calculate the new checksum. It's 11. I calculate the minimum amount that I need to add to it to make the checksum correct. That's 7. I actually compare D and W. I'll look at the more complicated case, which is when D is bigger than W. So here, if you want a puzzle, think about this puzzle. Think about why this is true. That if D is bigger than W, we restore the code word by adding a 1 immediately to the right of the leftmost D minus W minus 1 zeros. So here, you actually, if you think about, what's the right way to think about it? The right way to think about it is that you have, if you think about n minus, how should I, what was the way that I thought of thinking about this? You think about having n minus w zeros here and w zeros here. So you've got w1s here and d minus w minus 1 ones here. This solution is going to advance the parity check by the right amount. So that works out nicely. Comparison to prior work. Basically, the short story here is prior work sucks, as it always does. So the hardware solution, by introducing additional reads and writes, what it does is it increases the power consumption quite dramatically. And so that is our advantage over the prior work. We're certainly better than linear codes. Next steps. So here's a solution. It's actually a pretty nice solution. What about more shift errors? We don't know how to do that, really. So we have a solution for single shift errors. We're actually interested in other ways of making delimiter bits, other ways of fingering, let's say, 2 shift errors, and then thinking about how we might correct that. Again, we're interested in easy coding and decoding, because from the point of view of my collaboration with Dan, if I can't give him a circuit, like this code, the code that I showed you, it's basically got a carry-add circuit, right? If I can't give him one of those, it's not a solution, right? I can say that it's got fast encoding and decoding, but he sort of rolls his eyes. So we don't know quite how to do multiple shift errors. We're thinking a little bit about bit flips. Actually, what happens with bit flips is, on a very rare occasion, these magnetic domains, the wall between magnetic domains collapses. And instead of having 2 different values, you might only have 1. Now this might, it might not be a fully, we don't know enough about the physics to know whether it's really a bit flip or whether it's just zeros go to ones. But that is a relatively infrequent source of error. We can detect it when an input string passes the delimiter test, so we haven't inserted or deleted, but it fails the checksum test. So we can think about making codes for that. The other thing that we've thought of, are you going to show me? No. Is looking at racetracks in parallel. So could we do that? We could think, so we're still going to use our single error correcting code on one of these racetracks with the delimiter bits. And we could think about what happens when 2 shift errors occur. Well, we could think about detecting it, and we could think about erasing the corresponding racetrack. And then we could think about running a very simple code along the columns here. Something like a Hamming code, which is able to correct an erasure. So this is one way in which we could use spatial diversity to do something interesting. Actually, I should say about these, I mean, I'd actually never thought about insertion and deletion channels before I started working on Racetrack. And so, I mean, I discovered all of these old references, like the Ullman reference. There's also a very nice paper. So actually, there's all this work by Vashimov and Gallagher, and the work by Vashimov is incredibly complicated. But there's work by DeGarvey and Grossglauser on insertion-deletion channels that was motivated by packet communication and packet headers. And that's actually really easy to read. And there's a subsequent survey paper by Mitzenmacher, which is also very nice. So I should have said that at the beginning. All right, so that's Racetrack. And I mean, this is it's a cool, new physical substrate. And it's an example where coding theory can actually make a difference to computer architecture. I mean, we produce this very simple solution. And my computer architect colleague, he liked it. It was simple enough for him. So anyway, let me talk a little bit about Flash. So here, we go back to this. We've got this. We're trying to move this. We can't do that. All right, good. What's our solution here? What we would like to do, so in the coding theory community, there's work on flash cells with multiple levels. Actually really nice work. So there's some beautiful work. And there's thoughts of encoding information by relative charge levels, which is very nice. From the point of view of Dan, he doesn't know how to connect his computer architecture with that theory. What we do for him is we make little virtual cells with multiple levels. So what we do is we stick on our one-page X, we group, if you like, bits in sets of 3. And we make a virtual cell out of it like this. Now, those of you who have been in computer science a while, actually quite a long while, will recognize this as the Rivest-Shamir write-once memory. That's what it is. But you see, this offers a way of writing 2 bits more than once, right? Because you can write 2 bits as you go. You're at one of these states. You have a way of going up either to this level or to that one. Okay? So this gives you a way of implementing multiple levels. And in fact, this is one way of making a virtual cell. We're actually interested in other ways of making a virtual cell. But, I mean, Dan's point of view would be that, so we've created this logical or virtual MLC. And we can actually use it either to store 1 bit or to store, so here we're storing 1 bit in 4 levels. We could also use it to store 2 bits. That's the 2-bit representation. And here's what we're going to do. Let me explain how we're thinking about doing this, right? So so here we're writing binary bits, okay? And every time we change a 0 to a 1, or actually, I mean, we can think about a waterfall. Like on the previous thing, we had waterfalls. We went 0, 1, 0, 1. But every time we change a bit, we increase charge. And every time we increase charge, we're running out of room. So we don't like to change bits. Now, if I write n bits, I expect to change a half n bits. But is there a way of writing that will cause me to change fewer bits? So let me give you an example. So remember we have, so those of you who have taken a coding course will know about the perfect Hamming code of length 7 and dimension 4. So it's perfect. So the spheres of radius 1 about the code words, they exhaust the space. They're disjoint, they exhaust the space. So this offers a way of writing 3 bits in 7 bits. How am I going to write the 3 bits? I'm going to write the 3 bits as a coset of my Hamming code. That is to say, a translate. And I'm going to choose a representative of that translate with smallest weight. Well, there are 8 translates. One of them is just the code itself, so I don't have to write anything. The other 7 correspond to the 7 coordinates. So I've written 3 bits in 7 bits by only changing one of them, which is much better than 3 halves. So what we're going to do is we're going to extend lifetime by writing in a different way, by choosing a better representative. So this is called Kosek coding. And we're actually going to implement it with convolutional codes and the Viterbi algorithm for reasons that I'll talk about. So here, what we've shown at the top are levels of cells. So this might be the memory as it is now. And now I've got some new information I want to write. Well, all things being equal, I'd like to increment as few cells as possible. The thing that I most want to avoid is incrementing that red cell. So here you can think about what I'm doing is I have 2 objectives. I don't want to increment, but if I increment, I want to spread the wear uniformly across my cells. At the end of the day, when I erase my cell, I want pretty much all of those levels to be at the top, because then I haven't left any capacity on the floor. How do we do that? What kind of coding can I use? So this is, actually, one of the things that's been fun for me in this collaboration is writing up the papers. Because, I mean, Dan's community is ISCA, Micro, HPCA. And, you know, my community is the Transactions on Information Theory. You can submit a paper to the Transactions on Information Theory and you can get back a referee's report that says, cute idea, we're rejecting your paper because the proof wasn't hard enough. Whereas at Micro, you could get this review that you have to respond to where it says, you included a proof. Was that because the simulation didn't work? So in the Micro community, proofs are cause for suspicion. Whereas in the IT community, they are obligatory. And it's been interesting for us to learn how to write different sorts of papers. And so this is Dan's picture, how to create Kosek codes. I think that's the current memory state. What are we doing here? We're writing, I think we're right. All right, convolutional codes. We're not going to use block codes. We're going to use convolutional codes extending over the hundreds of bits in a page. They have a small number of states. we're writing a coset of a convolutional code. So there's something that there's something that we want to write, and we can choose any element of a translate of the code. So in a sense, what we're doing is we're searching over all the code words of a code. So the edges correspond to entries in that translate representative, and you can think of labeling them with costs. We want to pay a penalty for incrementing, and we also want to pay a penalty if we were already pretty charged up and we're adding some more. What we want at the end of the day, when we look at the distribution of charge levels across our MLCs, is we want to see a distribution that is biased towards the very top. We want most of our cells to look, we want most of our cells to be charged up. This is the Viterbi algorithm. Minimize the writes to the cells. We want to promote, this is called wear leveling in the Flash community. This is the little algorithm. We have the current memory. We have something that we want to write. That's, I'm sorry, wait a right. There's something that we want to write, which is, that's the old one. Okay, so this is the old state. And now we're going to produce this new translate. And then we use Viterbi to pick the representative. We write it in the memory. We keep going. All right. And here, actually, this actually appeared in DSN, so it's not submitted. It actually made it in. There's also, so I mean, this is one example. We can get this guy here. There are things that we don't. Did you? Oh, that's all right. Let me go back here. Let me go back. I'm not going to do that. That'll do. We actually quite like this. One of the reasons is that it extends over the entire page. So it's actually better than a short block code where you have to worry about the edges. We are thinking about product codes where the inner code is like this virtual cell and the outer code is this convolutional thing. We're thinking about what's the best way to distribute redundancy across the small inner cell and this big thing. So we'd like to understand how to do that better. We play with this Viterbi metric in various ways. One of the things we're curious about is, we run different workloads against the flash cell. And those workloads have different characteristics. Would it make sense to have different Viterbi algorithms? Or different ways of creating the cost function? Don't know the answer to that either. So those are, it's always good to conclude with things that you don't know. At the end of the day, we can produce this picture. We have some ideas about how to get information theoretic bounds. This problem that I originally teed up about how many bits do you have to write, you can phrase that as a rate distortion problem with respect to the Hamming metric, so you can say something about that. It's not exactly that problem because, you know, we write multiple times, and it's really hard when you do proofs to get an idea, to be able to model distributions when you do iterative things. We've also worked a little bit on PCM, so we've worked on how to lay out cells to minimize write disturb from one cell to another. So here, different lattices in 2 dimensions produce different kinds of trade-offs. Here, we've done some work on 3D DRAM, and this is another occasion where Ali Reza and I had all sorts of ideas for how you could do coding on 3D DRAM to protect against various things. And Dan looks at these ideas and he says, yes, he says, but the memory controller is distributed. There isn't a single memory controller that looks at all the channels. You can't do that. And so we got a new set of problems. Actually, this is really a busy week because I think the ISCA deadline is Friday and the DRAM paper goes in on Friday. So we're hoping that goes well. All right, that's it. Thank you very much for your attention. I'd be happy to take questions. Yeah. You know, I wouldn't want to stand behind exactly where the information theoretic bound lives. So you may be giving us too much credit for the 2x streamer. Mm-hmm. No, actually, so I mean, close, I don't know. I mean, it's been one of these technologies that people have invested in for like 5 years. I think that Stuart Parkin went to Max Planck in order to get it off the ground. You know, we'd like to help him. Yeah.
So with Flash, there's usually some amount of buffering where there is numbers between lines like
Mm-hmm.
pages, and then it does the wear leveling. It also there's typically a gathering of blocks into super blocks.
So one of the things that I didn't talk about that we did do in the original HPCA paper was to look more at the organization into pages and blocks and look at issues like, for example, write amplification, where you know you rewrite some things in other cells, in other pages before you erase that block. So those are, I mean, there's all sorts of opportunities. I mean, in a sense, the higher you go at every level in the stack, there's opportunity. And when you introduce something at lower levels like coding, you have to check that it doesn't screw up stuff higher up.
I'm just wondering if there are opportunities where you pick and choose which data you're writing here. There is this translation layer you can use in all coding because of that.
Yeah, we didn't want to touch the Flash translation layer. We wanted to provide a kind of virtual interface that it could talk to. So that's, in some sense, I mean, that was an important thing for Dan. So that's because we didn't want to change any of that software. There are, and actually, I mean, and so many of those have multiple levels, and they're very pretty. The thing is that when you have multiple levels, and all of those levels have to be distinct, and at some point you're going to erase, then you are going to leave a lot of capacity on the table, right? Because one of those cells is going to tap out, and the rest of them are going, if you had L levels, they're going to be L levels below. And so, I mean, we haven't looked at those codes with respect to this host visible capacity versus lifetime trade-off. But I think that that would be an important thing to do. I mean, one of the things that I hope I've gotten over is that there's lots of coding theory innovations, and in a sense, there's lots of computer architecture questions. And putting the two together is interesting. So this idea of host visible capacity versus lifetime is something that coding theorists in our community haven't thought about. When we represent our results, we represent them in terms of information theoretic capacity, rather than something that a computer architect would say. So I think that there is an opportunity to look at all of those things, and to take the best of both.